Hello, hi everyone. I'm Ramohan, working as head of the department in the Electronics and Communications Engineering department. I'm placed at Mahbubnagar Polytechnic. The topic we are looking into is the semiconductor diode. The subtopic we are going to discuss in this session is the formation of N type of semiconductor and P type of semiconductors. The objectives of our session is on the completion of the half of this session, you would be able to understand why I have to say half, because we'll actually review after half of the session, then continue with the rest of the objective to continue. So, on the completion of half of the session, you would be able to understand the process of doping. Then you'll also understand what the pentavalent and the trivalent impurity atoms are. Then we'll also see how the formation of N type of semiconductor is achieved. So we'll also look at the formation of the N type of semiconductor material. Now let us recap what we have discussed so far in the previous sessions. So we have actually seen about the intrinsic semiconductor, which is normally known as a pure semiconductor. Then we have also seen the extrinsic semiconductor, that is usually known as a impure semiconductor. So impure means we are adding impurities like pentavalent or trivalent materials, which is resulting in N type and P type of semiconductor materials. So we have also seen the comparison of between the intrinsic and the extrinsic semiconductors. Now let us see about the doped semiconductors. The process of adding impurities to the intrinsic or a pure semiconductor is called doping. That means we are adding impurities to a pure semiconductor to make it impure, and we take care about what impurities we are going to add. So the doped semiconductors are called as the extrinsic semiconductor, or also known as impure, as we have discussed. Then the impurities that can be added to a material are either pentavalent or trivalent materials. Now let us see about few pentavalent impurities. So the pentavalent impurities are those which have 5 electrons in the outermost or the valency bands. So in the pentavalent atoms, they will have 5 valence electrons. So these impurities or these materials will have the capability to donate electrons to the conduction band of a semiconductor atom. And because they are able to donate electrons, they are also called as the donors or donor type of materials. And normally, let us see what materials have such properties. So the material here is phosphorus, which has got 5 electrons in the outermost orbit, then arsenic and antimony. Okay, so the materials like phosphorus, arsenic and antimony are very commonly and used in the industry to create one donor type of metal, that is N type. So let us see the atomic number of phosphorus. It is 15, and by the structure we'll see that the outermost orbit has got 5 electrons. Look at this: 1, 2, 3, 4 and 5. So this is what happens. So there is a nucleus and a number of electrons, and in the outermost orbit there are 5 electrons which are orbiting around that. So these electrons will be useful for us in the process of conduction. We'll see how we make use them. Now let us see for a trivalent materials. So trivalent atoms have 3 valency electrons. That means the outermost orbit has got only 3 electrons, and these atoms accept electrons from semiconductor materials. And because we are telling that they are going to accept electrons, and so these are also popularly known as the acceptors. Let us see the materials that have such properties of accepting electrons. This is aluminum, boron, gallium and indium. So these are commonly used impurities with trivalent and that are used in the industry. Well, let us see the example of a aluminum. One of the example what we are going to look into is aluminum. So the atomic number of aluminum is 13, and as per the structure, the outermost orbit here will have only 3 electrons. You can see the structure of aluminum here, the molecular structure. So it has got 3 electrons, as you can see, 1, 2 and 3. How does it function? So this is what the structure is, and it is going to work as you can see. So we should remember that they have only 3 outermost orbits. Now let us see into the subdivision of the extrinsic semiconductors. In the extrinsic semiconductors, further we have 2 types depending upon the impurities that we are going to add to that. So the first one is the N type of semiconductor, then you have P type of semiconductors. Let us see how this N type semiconductor is. When we add a pentavalent impurity to a pure semiconductor, we will get N type of semiconductors. Here, the doping is done by adding the desired impurity to the pure semiconductor when both are in a liquid state. So let us take a small example of adding impurity to the silicon, and the impurity we are going to consider is the arsenic. Okay, so here we'll see. So we have taken one pure semiconductor substrate, and then I have taken another small piece of impurity, that is arsenic. Now we are going to add them. So that is how it is. So when you add up this arsenic to a pure semiconductor, that will result in a N type of semiconductor material. Let us look into the structure of this one. This is the structure of the arsenic semiconductor, which is added to the pure semiconductor, and the resultant is a N type. So this actually denotes the resultant structure of the material. And we know that the arsenic has got 5 valence electrons, and it makes the covalent bonds with adjacent 4 electrons of the silicon atom. The fifth electron becomes free and enters into the conduction band. As you can see in the figure, there is a free electron, and arsenic is there in the middle of the structure. So after sharing 4 bonds into the with that of silicon, it is left with one free electron which is freely available. So this is how we are able to create a free electron in a pure semiconductor, so that will be useful for the carrying of current or the electron flow. The fifth electron here becomes free, and that will enter into the conduction band. And the pentavalent impurity atom donates one electron and becomes positive donor ion. That means the arsenic here, you can see there is a small hole in the middle. So that is a hole, it becomes positive now. So further looking into that, some of the covalent bond breaks also due to the temperature increase and generates an electron hole pair. So electrons are now becoming the majority carriers in this n type of material, and the holes are the minority carriers. Now let us look into the energy band diagram of the n type of semiconductor material. Okay, yes. So this is the valence band, and here comes the conduction band of the n type of semiconductor material. And where does this Fermi level lie? Let us see, where is it? Yes, so it is very close to the conduction band, as we have studied earlier in the previous sessions. So we have to remember well that the Fermi level here lies near to the conduction band of the n type of material. Now, n type of semiconductor material. Some points to remember about this. So the addition of each impurity atom donates one free electron into the n type of material. The addition of each impurity atom donates one free electron to be available in the conduction band of the material. Now, the free electrons created so due to the addition of the impurity atoms are called as excess electrons, because they are no more existing there in the covalent bonds, and the fifth electron is coming out, as we have seen in the previous structural diagram. So there are excess electrons, and the number of excess electrons are made equal to the number of impurity atoms added. So that is how you can control the we can control the impurities, or the indirectly we can control the number of electrons that can be made available for the flow of current in the semiconductor material. Now by adding this, what happens? By adding more impurities, thus we are actually increasing the conductivity of the semiconductor material. Now let us see the electrical representation of the n type of semiconductor material. If you look into that, the red positive is positive donor ions, and you have holes. Then we have free electrons. So proportionally we can check there how many free electrons are there. So many, as we can see, there is one hole. So there is a positive ion. We don't have negative ions here in n type. and then you have electrons and also holes. Let us summarize the points we have been covering or discussing throughout this session. We have discussed about the doping of material and the process of that, then doping of a semiconductor. We have seen the pentavalent and the trivalent impurities, and we have also discussed about the n type of semiconductor materials. Now let us just see a small quiz or recall our memory. Which of the following material is a trivalent type? Phosphorus, arsenic, or boron? Which is that one? That is boron. That is a trivalent material. Which of the following material is a pentavalent material? A is boron, it cannot be. B is arsenic, and B is arsenic, and C is gallium. It is arsenic because in the previous example we have added this arsenic to a pure semiconductor silicon material. Majority carriers in n type of material are A holes and B electrons. Naturally they are electrons. Let us look into some frequently asked questions in examination point of view. What is meant by doping? What is a hole? Describe the formation of n type of semiconductor. What is doping? Doping is simply adding of impurities to the pure semiconductor, thus to make it a impure one, and it can be a trivalent or a pentavalent. Depending on the requirement, you can go on adding the response to this question depending on the marks. Then what is a hole? So from an bonding, if you are removing one electron, then one electron is lost from the material. So there is a hole created, and that vacant gap is called as a hole. Normally lack of electron here in this material is denoted as a positive ion, thus that is a hole. So a hole is a lack of electron, lost of an electron, and which is again indicated by a positive amount of charge equal to one electron. Now, what is the third one? That is the formation of n type. How is it? How does it happen? So it is by mixing an impurity of pentavalent to the pure semiconductor. Okay. Now let us continue with another session. So here we will be looking into the p type of materials. The main objective here is this p type material. So on the completion of this session, you will be able to understand the p type semiconductor materials and the energy band diagrams for the p type of semiconductor that is thus generated in the process. Well, let us recap the topics we have discussed in the previous session. So we have actually discussed about the formation of the n type of semiconductor. We have discussed about the charge carriers available in the n type of semiconductor. Then we have also looked into the energy band diagram for the n type of material and understood the presence of a Fermi level and also its location. So we have seen that it was lying close to the conduction band. Now, similarly, let us discuss about the P type of material. Let us see how we are going to actually generate or prepare a N type of semiconductor. So when we add trivalent impurities to a pure semiconductor, we will get a P type of semiconductor. So the impurity we are going to consider is gallium, and we have taken a small substrate of pure semiconductor material. Now let us go with the process of adding, as we have discussed earlier, mentioned it. So we'll be actually doing this process of adding impurities to the pure semiconductor in a molten state or a liquid state. So when you add up this, the resulting is a P type of semiconductor material. Now let us go and see the structure for the P type of semiconductor. As we have considered for the N type, let us look into the structure. So here you can see that there is gallium in between, and that is a trivalent material, and three of the electrons are sharing with the covalent bond of the silicon material, and there is one hole, means shortage of one electron in the material there. Okay. Here the gallium atoms have three valence electrons. So the gallium atoms have three valence electrons. It makes covalent bond with the adjacent three silicon atoms. Then you can see in this structure that there are three which are sharing with the silicon's covalent bond. Then there is one shortage of electron to share with the covalent bond. So there is a deficiency of one covalent bond in the material, that is electron, and this is what is denoted as a hole. So by adding the semiconductor impurity, that is of gallium, it has resulted in a creation of a hole. So what does that mean? That means it is deficiency of one electron. So the adding of trivalent atoms will make the material into a acceptor type. So they accept one electron because it needs one to share with the covalent bond. Now hence these are called as the acceptors. So the trivalent accepts one electron, and these are called as acceptor type of impurities. In addition to this, some of the covalent bonds break due to the temperature, and also the electron hole pairs are generated in the material itself. So the holes are the majority carriers in this P type of material, and hence normally, as we know, the electrons are the minority carriers. Now let us discuss about the charge carriers in the P type of semiconductors. So you have negative acceptor ions, means you have more holes, that means it is going to accept the negative acceptor ions. Then you have holes, then you also have few free electrons which are minority carriers here. Now let us see the energy band diagram for the P type of semiconductor. What is that one? Lying at the lowest level of energy, that is a valence band, and there comes the conduction band. Then where is the Fermi level? So we can see that the Fermi level is closer to the valence band. Yes. Now let us summarize the things what we have discussed in the second half of our session. So mostly we have here discussed about the P type of semiconductors. Then we have also discussed about the majority carriers and the other carriers available in the P type of material. Then we have also seen the energy band diagrams or energy band levels in the P type of semiconductor material. Let us see a small quiz. The following material is to be added to get a P type of material: trivalent and pentavalent. Obviously that is trivalent. The majority carriers in the p-type semiconductor are holes or electrons. That holes. The frequently asked questions normally in the examination point of view are the following: explain the formation of a p-type of semiconductor and draw its energy band diagrams. Now it can also be asked as a compare the N type and the P type of semiconductors. So with this we conclude this session, and thank you for that.